Preguntan al son.
Yo no llega ningún mail.
No llegaron.
Recording in progress.
Okay, so today we are going to apply the knowledge that Alex explained the lesson before about neural networks. We will try to implement a small neural network, and sometimes it can get a little bit messy with the nomenclature and with all the vector and matrices. So first, I will do a quick recap about how these matrices are constructed, so we all can remember that. So if you remember, we have a matrix X, which contains our data. So a big matrix, and you remember which size is going to have X, how many rows it's going to have, and how many columns. Anybody?
Columns is the feature.
Yeah.
And the rows are the number of.
Yes. So in rows we have, we can call it M, the number of different data we have, and in the rows we have different features.
We still don't. I think we don't have access, or at least I don't have access to the material.
Yeah, they will upload it now.
They're upgrading, yes.
So we don't need it for the recap. Okay, and this for classification, we have matrix Y, which is related to X, and has, yesterday we saw that had the, for linear regression, had the same number of points of rows. So it has one for each data that we have. And it was just a column of ones or zeros, depending on if it was the first class or the second. But when we extend the code for multi-classification, which Alex explained today, we can see it as instead of one column, we have multiple of them. So if we have three classes instead of two, it would have 3 columns, 4 classes, 4 columns. And they are all zero except one, which represents that it belongs to that group. And so on and so on. So it has K classes. And lastly, how are the parameters that we are trying to optimize? It's x times theta. So what is the shape of theta?
The number of samples times the number of features.
Yes, features and not samples, but features and classes. And this was related to the image that we saw of a neural network, that we have many inputs. And for example, two outputs, we have, or three outputs, three different classes, and we have one theta for each of them. So we have a matrix. But when we add more layers, they are all connected. What will happen is that instead of just one matrix of thetas, we'll have one matrix for every layer. So we'll have here another matrix and another matrix of thetas. And so on until the last layer. So now the sizes of the thetas. In the first theta, we will have features, and in the last we'll have the number of classes. But in the middle ones, we'll have here will always be the next layer size, let's say. Next layer, next, and so on. We're having the next, and here we will have the previous. So we know this. It's important to understand this so we know how we are going to multiply our vectors and our matrices. So we don't mess up things. So, to minimize neural networks, we have to do forward propagation and backward propagation that I also explained before. And forward propagation is just to propagate the inputs through the layers. It's just applying every theta at each layer. And backward propagation is to compute the gradient reversely from the output to the input using the chain rule. So in forward propagation, we said that we were going to save the outputs at every layer of the sigmoid function. So we later in the backward propagation can use the property from sigmoid, which the derivative is just sigmoid times 1 minus sigmoid. So we don't have to compute that again, and it's fast. It's much faster. Okay. So with this, I think we can start. We can do a recap of the equations. Okay, so the equations that we had, these ones are the same that we used yesterday, the hypothesis function, the sigmoid, that now it got an A instead of the letter sigmoid because A goes for activation function and it's more general, so we can use, here we could use any activation function. We could use sigmoid, or we could use hyperbolic tangent is also used, ReLU, who also Alex talked about a little bit. But sigmoid, it was the one used when neural networks were firstly introduced into this world. and it's okay. But later they improved the performance adding Relu. So for today we will use sigmoid as well. And then we have the cross entropy or negative log likelihood, which takes the sum over all the samples and sum over all the classes. We have the derivative of the sigmoid, the derivative of the cross entropy, and these are the deltas, the formulas for the delta that Alex explained through backpropagation. So we are going to use those. Here is just like a little pseudocode of how backward propagation works. So you start in the last layer, you always will compute the derivative of the outputs, the activation function. And in the last layer, if we are in the last layer, we will multiply it by the gradient of the cost function. If not, we will multiply it by the delta, which is like the accumulation of the gradient through the layers. The dataset that we will use today is, first we will use the same as yesterday, which is the microchip, because it's really good to see your fitting and all that stuff. And later we will use the iris dataset that Alex also introduced this morning. It's multi-classification because we have 3 groups. Each one of them is a different type of flower. And in the features are sepal width and length, and the petal width and length also. So this, I talked a little bit about it yesterday. This is the correlation matrix. So we can see the pair of features, how they behave. So we can choose the one that we think is the best for our classification. And these 2 features, feature 3 and 4, seem really easy to classify, much more than feature 1 and 2. So it's better to choose our data, how we represent it, and we will represent it with x3 and 4, for example. So we can start with the code now. It's uploaded.
Yes, yes.
Okay. So like the other days, we open it and we import the datasets. P3 iris, P3 microchip. And we can just run the first cells, which are the same that the other days. One for the data, for the plots. This cell also, which is the gradient descent that we coded yesterday. And we can see the data.
In the Zoom, we are seeing this, like we're not seeing the code.
Oh. Thank you. Okay, you see now. So I just said that we run the first cells, which are the same for yesterday and the other day. The gradient descent that we coded with the step update and the while loop. And we can run this cell, so we see the data is the same as yesterday. And now what we have to add to our code are the derivatives of these functions. Yesterday we coded all these functions. We said the hypothesis function is x times theta, the activation function is this formula, cross entropy we coded, and later we introduced this so we prevent overflow, and we also coded regularization. But today we need their derivatives because yesterday we applied the gradient directly because we knew the formula. But today, as we are applying chain rule, we need to multiply every time for the derivatives. So you have 5 minutes, 10 minutes to put the formulas here for the G derivative, cross entropy derivative, and regularization derivative, which are the formulas that you have here. Okay. And I will come around and try to help you. And remember that this multiplication from the derivative of the sigmoid is element-wise. Okay. Recording marcado y todo.
The J function where una pregunta. ¿Es el residuo donde se encuentra en la regularización? ¿Dónde se encuentra en el TD?
Sí.
Pero bueno, esta derivada es esta, ¿no?
Pero no son las no sé.
Gracias, que no.
Bien guardarlo como se llama.
Ya, pues no sé.
Organizando las
Se ha ido o bajo.
Sí, 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 lo hacemos que
Claro,
Porque no es solo.
No, se puede computar esto para poder correctar.
Ah, el cluster, vale, vale.
¿Esto se tiene que hacer la suma o lo puedes devolver directamente? No, tendría que ser un tensor solo.
Sí,
Tenía muy claro.
sí, tiene que ser un solo término en ese caso. Depende, o sea, es que,
Entonces te le falta la suma aquí, ¿no?
sí, porque teta no es un solo término. Ah, vale. Mm. Se me hace muy separado.
Okay.
No. Claro, no, sí, es tío, no sé, o sea,
Okay. So most of you already put it.
tal vez así.
Derivative for the sigmoid will be just c times 1 minus c. Derivative for the cross entropy will be t minus t. P times 1 minus p. And the derivative for the regularization is just lambda times theta. So we can run this cell.
In the derivative of the derivative function.
Oh yes, thank you. Here also.
I was about the z. Isn't g derivative equal to g times 1 minus c?
No, because as we said before, we can. I said before, we will take profit that we have already computed this formula, so we can just pass directly the values.
But isn't it theta just the parameter that controls how smooth is the sigmoid, but not the...
Yes, but when we are calling the activation function for
You are doing the sigmoid of the sigmoid.
what?
So theta, the parameter theta in this case, what is it?
It's already sigmoid.
It's already
So,
sigmoid.
yes, we could put here if statement, so we don't compute this again because we already have computed. When firstly we will call just this part of the equation and later this, and we can put an if, or we could define the derivative of the activation function in another different function.
Okay.
T is for theoretical or
In here, target. T prediction, T target.
yeah, and then looking what you have above, it should be their target is y hat.
No, target is Y.
Yes.
Prediction is Y hat. Okay. So now we will we just have to use these formulas to compute forward propagation and backward propagation. And once we have forward and backward propagation, we will just call the gradient descent method that we used yesterday, and we'll have our neural network. So for forward propagation, I already write the loop. So we have to topology is what Alex called this morning architecture. You can call it architecture. Sometimes it's called topology. So, for example, we usually give it as a vector. Topology can be, for example, 4, 8, 8, and so on. And in the first layer, you need a number that matches the number of features. So, for example, let's say that we have just 2 features. And in the last layer, you need to match the number of classes. So 3, if you have 3 classes, for example. And this would be our vector of topology. This means we have 2 inputs, a intermediate layer with 4, then one with 8, another with 8, and the last one will be with just 3. And from here, we will get our outputs. So for the forward propagation, we have to pass from the beginning to the end. So we take a fourth of the length of this vector. I already put the formula for the reshape. It's a little bit unnecessary and tedious, but it's just that theta is a vector and we need to reshape it in our matrix. So we have that, and here below the cont line, we have to put our forward propagation, which will be at every layer, we will compute the hypothesis function and then the activation function or sigmoid. And we do this every time for the loop. And at the end, the last activation that we get is our output of the forward propagation. So also here the function returns J and A. So J is the cost and A will be the matrices that we have saved through the forward propagation to afterwards pass it to backward propagation. So J, after you have your last activation, J will be just to use cross entropy or negative log likelihood with your last activation, let's say A minus 1. And A, the result from activation, you have to save it every iteration, so you can also return that list of matrices. Okay. And 5 minutes to try to program the forward probe. Any questions, you can ask me.
How we should set it as a metric?
A. Okay, so we already defined A1, which is equal to X, because our first layer is X. And then every time that we want to save it, we just say A append, which means add to the list, and what we computed.
And we have
A list of matrices.
and numpy matrix.
Yes, exactly.
J is the total cost.
Yes.
La segunda, vale, y la realiza. Yo tengo que calcular al final.
Sí, guarda el loop. Porque
Y
ya tens
la,
l'última.
i el comptador, llavors,
El comptador és per les tetes, perquè cada vegada...
Sí.
Sí.
com el que
A saber si fa.
Però bueno, i cada vegada només estàs pillant un calcio.
perquè el que us sigui vostè tan empresa.
Perquè així com la és una llista de matrius, la tira és una llista de matrius. Pilles la longitud de la red, la construeixes.
Sí, però per què...
Cada vegada agafes aquest valor i aquest valor i muntes
I aquí agafes el comptador.
Sí.
És una forma de guardar Z.
Sí. Okay, also, when you call a function that gives two outputs, for example, we define it that all the functions give us are the value and the derivative. So when you don't care about one of the two outputs in Python, what we use is the underscore. So for example, let's say you call the activation function or the sigmoid, I don't know how it's said. We know that sigmoid returns sigmoid and its derivative. But in Python, what we say, if we don't want this value, we put an underscore. So it don't give it to us.
Ahora sí, claro. Lo que eso entiendo, pero o sea, entendería que sigue ese primer paso. Sería consciente.
Cadascú fica el nom a la funció com li surt.
Tu puedes regular de persona forward propagation.
Ah, es verdad. Sí, lo olvidaron.
Aquí TCL no usan nunca, pero esta interfaz, Fernando no tiene perfecto.
Tenemos que hablar cuáles son los resultados.
¿No? Hay
Fuera, creo.
¿Si lo usas o cuál usas?
Sí, porque ya tienes que tener las as, pero aquí tenía hecho en esto.
Muy duro, muy duro.
Este es el que se ¿no?
No, yo lo he visto y ya.
Afuera, está fuera del for, ¿no? Pero como tú habías dicho, esta activation function, pasas la multiplicación, porque h es solamente x por teta.
Why? Why did you think?
Entonces he querido probar una cosa que es mierda.
You're multiplying every time x times theta.
So it's
Entonces el círculo que tienes que buscar.
But you have to specify which a.
A of the current.
AK.
De momento,
Otherwise, you wouldn't have like a connected network. You are just have a lot of.
Okay, so the connection with the first will be the
You
first.
were connecting everything to the input layer.
Okay.
Uno más, uno
lo último que
No, con entropía aquí ya. Igual es el rostro. Pertenece. Però guardar un historial per veure com minimitzes i aquestes coses. Sí, o sigui, podríem no calcular-ho, podríem només guardar els outputs i per backward propagation estaria bé.
això
Podries tenir una funció a part o...
Pero fíjate, eso de hacer lo que te da la gana.
No, es una plantilla nomás.
Sí que purificarías cada
Vale, està bé.
Per això no m'agrada que doni dos sortides.
A mi tampoc m'agrada.
esto me volvía J, entonces además se volvía.
Iba a escribir.
Es lo que vamos a pasar.
Porque ya está bien.
Sí,
Pero no volia...
al hipótesis se lo pasas y después aquí haces.
El cambio que está la computadora de abajo, pero que tengo operando más.
Tampoco hay una de esto por una
Actualizar.
La última.
Claro, la pantalla es
La última.
Y digo, Fernando,
una clase de alertas. Una clase de alertas.
Viendo esto de
Tampoc massa codi complex.
Aparte,
Vale, ok. O sea, pero en realidad lo único que necesitas es el
¿Qué está regularizado?
Esto es
Ah, para comprar la total.
También tengo los círculos.
y el otro.
El castigo no está manchado.
Lo vamos a estamos haciendo una vez para después utilizar.
Y creo que todos los de la la regularización.
Claro, que se da
Acaba de acabar a mitad.
Ah, vale, más la suma.
O sea, esto lo podría no es. Puede ser que sí, porque si ya estamos llamando a por eso.
Okay, so most of you already got it, so I will put it for the ones that haven't finished.
Porque chártelo.
First we have to
Lo que
go to
estoy
the
no quiero leer
function,
eso porque no entendí mucho la verdad. Es el último.
and we will use a. We can put here -1 or k. We are using the current a multiplied by theta. And then we compute the activation function. We save it. Okay. And after the iteration, we can compute the loss with the cross entropy. With the last state, so -1, and the predictions, which is y. And also the regularization term that you forgot about it, most of you. And the regularization, we can put it inside the 4 and compute it for every layer, or we just can use, as theta is a vector, not theta reconstructed, but theta, and we can just pass it like that, and it will be fine, unless operations. So J is L plus R. Okay, so now we have just to define backward propagation, or abbreviated backprop. Backprop uses these formulas from delta. In the last layer, delta will be just the gradient of the cost function times the derivative of the activation function of the last layer. And then every layer will use the previous layer, the previous delta to compute it. And the formula is just times theta times the derivative of the current activation function. It has to be something like this. It's a reverse loop because we go from the last layer to the first. So while I greater or equal than 2, compute the derivative of the activation function. If we are in the last layer, compute the derivative of the cost function. And if not, use the other formula of delta. And the gradient will be A times delta. Okay. So implement it, 5 more minutes.
That's for the back propagation.
This is backward propagation. Yeah.
Hi ha algú que hauria fet diferent.
Instead of the if, you would have put that outside.
For que sí que ja li fiques el 2 en lloc del 0, perquè te'l trenques. Si no has de ficar un més gran, o sigui, if menys petit que 2, break, o si fiques que faci fins a 2 ja està, t'ho farà més petit que 2. Vull dir, si t'han de ficar...
Però jo no he ficat ningú mail. A veure, deixa'm mirar.
Jo potser m'equivoco, però llegint així ràpid.
Esto es... A ver, es que nosotros explicaremos la matemática. Sí, eso llamamos delta.
Delta.
Sí, mira.
Bueno, a ver. Primer, es un 2.
Ah, es verdad, es verdad.
Me has de pensar que en Python sería un 1.
I aquests
Y el 3 se puede hacer en
mensual protocol. L'entens,
Sí, sí, sí.
El comunitat d'aquí sembla que
Está diferente.
La hipótesis.
Yo también un poco el gradiente, la función, lo que viene del vector centrópico.
Lo que te decía el otro día, cuando vi con el caso, y corregí.
Es lo que no sé, eso justo estaba pensando exactamente lo mismo.
Y ahora lancé con la otra vez.
¿Cuál?
La edición de mi lo que orientación.
Sí, o sea, es en... Después lo deberíamos de pasar.
Y sale lo mismo. ¿Cuánto tardaba esto? Que no sé, que no me...
Escriban una A y pensé que yo.
Vale.
Estaba muy poco. Sí, sí, pero hasta la vida. A es una lista de datos. Una lista anterior. Estás frenando y super corto. Aquí, total.
Me dejé conectado al wifi de la PC. No puedo, solo desde el Chrome.
Está brava. Ya es la Sí, però jo ho fa això en cas de...
Okay, so I put it on the screen, the last few lines, because I forgot, I wanted to put it before, but we have to also play around with the shape of the gradient. So I just put it. We need also, like we did here, to reshape theta, and we need an auxiliary variable. We have to do the same with the gradient, because we want it in a vector shape. Someone you suggested, and of course it would be much more optimum that we had a function that always transforms from vector to list of matrices, and we could call that function every time.
Yendo con el mismo internet. No, que 16.
Lo vemos después, después de clase lo vemos. ¿Cómo lo corriste?
Es el primer que es la
Perché questi testi ben completi.
Guarda la delta.
De cada punto.
No te sé mucho.
Pero fue la iota que era derivada.
Ya lo tienes.
Entonces ahí desde el L pero quieres guardarlo de esta vez no hay visto una P. Sí, pero una P es
Creo que se cambió algo porque
es la última. Guardant davant. Si no, després potser també servir, però després has de saber que els índexs estan erroris. Sí que no ha pensat.
Si la pen no
Clar, el Apple te faria que la última està la primera. Si fas l'insert
A la segona, ya el que busca la funció del vector, ¿no?
Sería la línea.
La regularización siempre le se contempla cada cálculo.
Sí, no, o sea, digo, cuando estamos aquí, digamos, cuando estamos haciendo LEDs, digamos, DI, DI más 1, multiplicado por ZDI. Tenemos una variable gráfica y entiendo yo.
El resultat diria
Sí, he posat un punt. Vale.
No sabia com veure.
No, és mirat.
Que és...
Integrat en si.
En principi,
Ahí se acaba de
descarregar
¿no? detectar.
producte fundamentalment
Els apunts podeu posar
Es el del cambio de sonido.
o
aquestes matrius, no?
les matrius, si és un punt. Però d'on ve ja sí que és més complicat. Ho has de pensar amb la derivada que ha explicat que l'Àlex va ser un poc ràpid, però que tampoc s'entenia. Que és tota la derivada aquestes ridícules.
Sí.
Ho pots fer així, però després quan l'usis t'has de recordar que tindràs els índexs al revés. Perquè la delta realment és l'última delta. Sí, com nosaltres ordenem la delta, primer calculem l'última, és la 4, després la 3, la 2, la 1, i si tu fas append, ho estàs fent al revés.
Sí, però bé.
Si després utilitzes l'índex B,
S'ha darrere que
vale.
realment aquí
Sí.
no la tornada.
No, sí, així està bé.
Més que de fet no em portaria vull dir, si podrà només d'aquesta...
Sí, no em portaria guardar la veritat. Podríem usar cada vegada que...
Bé, no, perquè...
Bueno, no, sí, perquè el següent for la necessites.
Sí. Podria sobreescriure.
Ah, sí, podria sobreescriure, ja està.
Sí, no vull ser prou de la solució.
Però perquè no ho entes, perquè és massa complicat.
Exacte.
Ja. Perquè el forward també l'heu copiat.
Sí.
Pregunta, no?
Sí, més o menys. Sí.
Si vas passant per les capes, cada vegada fas hipòtesis, sigmoide, sigmoide, arribes al final i amb l'última de totes fas l'error, que és el procentropí. I el backward block, bueno, és la regla de la cadena. No és difícil d'explicar encara, però és la regla de la cadena i cada vegada es multiplicant. Per la derivada de la funció d'activació, per la derivada de beta, o sigui, no multipliques per beta, per la derivada de la funció d'hipòtesis. Multipliques per tot, ho vas acumulant i ho vas guardant. Però bueno.
Sí, més o menys. Em seguim. Sempre s'ha de fer-ho. Sí, buen punto.
Esto es...
Sí, vamos a hacer
Esto es lo 49. Yo creo que...
no sabes si tu maestro
Tú me pasas claro, no te voy a puedes comprobar cómo es eso. ¿Cómo guardas aquí?
¿Cómo te falla por contexto?
Cuando yo leo el último, pues no hacer interacción. No puedo sacar el último. Ah, para eso entre el último y el primero. Vale, entonces vale.
Okay, so I have put the solution in the board, but it can be done in very different ways. So, for example, I used delta insert to have the same structure of deltas that we saw in theory, but you could just use append. Some of you told me, and here you just call the last one that you have been introduced, and it's also okay. Or you could even don't save delta and rewrite it every iteration as well, because you just need the last delta, so you use it and rewrite it all the form.
The index of theta L shouldn't be backwards as well, like the one in the gradient. So
In the regularization.
no, when you are calculating theta L, it shouldn't be theta from cone to cone for topology k minus 1 times topology k.
No, actually not, because I think, let me think, I will draw it so I can see it. But you have the network. So to compute this gradient, you are not using this theta. You are using the outputs. And to compute this gradient, you are using these outputs, which are theta times this.
Maybe you're because K is the loop is going backwards.
Yeah, I know. But because you have two thetas. Let me see the formula. You see, you're using the theta I to compute gradient I minus 1. And this comes from the chain rule. Yes, because I'm trying to think how to explain it. But look at this statement. It's in, we are just doing it if it's not the last layer. If we did this statement in the last layer, we would be taking theta plus 1, which would be theta here that doesn't exist. And that's because we are delta is accumulating the chain rule. But when we're computing this gradient, what we save is the output from here. And when we move backwards, we multiply this output by this theta. And when we move backwards by this theta, and here in the last layer. Okay, so if it's right, we can now doesn't matter, and we can run the same script that we used yesterday. We define a d, lambda, the index is, I will explain it later, it's for the multi-classification. And we can also define some hidden layers. So first we can try with just d equal to and no hidden layers. This should be similar to actually, if we are not using any hidden layers, we are gaining again the just logistic regression. And then, like yesterday, we define a function for the cost function, a function for the derivative, which would be backplot. The cost function is forward plot. And we use gradient descent. And this is in fact what we obtain for minimization with d equal to. Are you seeing this plot, all of you? You have an error? Could you run this cell or no? Who can run this cell? Raise your hand. Okay, I will come to see what errors you have.
Espero que sea esto. Sí. ¿Era esto? Estaba. Amplia rayas, ¿no?
Así todo raro.
Una amplia raíz, ¿no? No, ya, pero no. Sí, es paréntesis. Aquí, mira.
Es una multiplicación. Un error de tamaño.
Sí. Take
Eso es Visual Studio.
no special.
No menos uno.
Sí. Voy a decir multiplicar por cambiar.
Sí, vale.
Funcionarías, pero no sé si eres.
Sí, es al revés, creo que 6 per theta. Sí, sí, 6 per theta.
Errors.
Tamaño. Okay. Insert expected. Where is the answer? Here, okay. 0, comma. Because you want to say in which position you want to insert. Sí, es en aquesta línia, però estem mirant les solucions entre una d'aquestes matrius que són no s'adenten. You have it right?
Yes.
So can we see
The back approach.
nosotros pues vamos vale, sí, pues una baja. Es que no.
Es que muy largo también.
Okay. You can see me, right? You like different values. That's really overfitted.
Yeah. I was playing also with this.
Yeah. Not too far. Look at my no puse el top, a ver si alguna cosa. Can you show us the back prop as well?
¿3.7? 3.5 está hecho. ¿Te abres algo?
Seems
Tengo la 3.10, pasa que no creo una carpeta aparte. Son cositas nomás, tengo de versiones.
ja que t'acord, prova de tornar a córrer les... I ara corre les... No falta que tornis a córrer les que ja es corren.
Pero ya no carga librería porque no sé si directo hasta ahí.
Nada, pero este está bien. Si quieres hacer algo por ti. Pero yo creo que cosas más grandes.
Creo que se cruza en esta línea de mitad, donde podría ser un error.
Aquí no tienes que hacer con el descargar y después seguir haciendo cosas.
Como he dicho,
Tengo un
Sí.
es el learning rate. Lo vaig solucionar ahir. Sí, potser sí, perquè si ho pones un 5,
Perquè no agafa l'últim element com ja dic abans.
rate is 0.1, yeah.
Viste tal borre, que és que
Claro, perquè jo ho estava fent amb 0.6.
Sí, claro.
But when you run it many times, you save
Algun error hi ha, perquè jo això...
A mí esto me da desconfianza. Tú,
Si lo irà sí, tio. Aquesta imatge ha estat posada.
raro es que esto se está convirtiendo.
Està minimitzant el partit de comprar-la. Baixa una mica. Perquè un diu que està en error. O sigui, fixa't que minimitza, convergeix i al final li és passa el que hem dit abans, és una mica massa alt perquè no l'hem reduït el learning rate i pareix que explota al final. Però com fresaros que no li passi, no ho puja. Prova de baixar i farem el problema molt més fàcil. Ja està, i 4.
Punto 1.
Si te interesa usar, no vale la pena que lo uses.
Sí, però com no està acabant de funcionar, algo malament. Hi ha alguna
A ver, si algo te está pasando al final, te está convirtiendo, después te...
Las operaciones están bien porque funcionan, pero hay alguna que está mal.
En la montaña que se ha caído.
No, porque soy good running.
Bueno, vas necesitando las
But now I was using a different epoch.
Tens error també.
Sí, no, no basta.
Por ejemplo, empecemos, vamos a empezar este 3, que es el primero que modificamos.
Igual el día de
Aquí está. Ahí tiene que ser cerrado. Mejor. Porque si no estás, en teoría tienes que utilizar el sigmoid del sigmoid. Ahora corre ese, si no corre todo.
que hay un error, es que es un cambio americano.
Bueno, no sé. A ver cómo te salió tu video.
Sí, pero eso no tiene.
Pero como tengo 24 con la mano,
Claro.
no
Bueno, yo también tengo.
Depende
Ah, el un rey creo que no lo modifiqué yo. Ah, no, sí.
No.
Que lo hice, nada, es igual que tú para verte.
Bueno, faltan 2 minutos.
A ver, podemos poner lo que estaba en 2000 ya. Un rate.
Fíjate que solamente
Sí, ¿verdad? Lo demás.
tenías punto 4.
Ah, a ver, dame un segundo, déjame.
Sí, bueno, pero igual es que es una
Porque aquí da seguida.
Y ese primer punto tienes toda la
No, es que no más.
Pues tiene todo uno, bueno, sí, más o menos. Y aquí 1.4.
2000.
Cambia un poco y igual no sé.
Ah, vale, sí.
Exacto, no sé si la. Exacto, entonces ahí no puedo quitarlo. Mira.
Aquí da igual.
Mira. Sí, ahora me cambió por completo.
¿Es la mateixa línia?
No, ara.
Vas a hacer el random de los tres.
Cada dia. Esta fórmula sí que l'has copiat. I el resultat també l'has escrit.
Sí, però no l'escric.
Vale, doncs també llavors amb els índexs.
Yo no sé un tico. Están buscando.
Yo copia dos.
Què diu?
Esta otra range que está aquí.
Quiero ver al menos qué hace.
Tuve tiempo de hacer el de que descargan por la copia esperar. Lo veía fijo. Errores para parece un camello.
Nunca mirado.
Y es que es el.
Max de Fox.
És raro perquè això ja estava al codi, no?
On s'ha avançat tot. Mira, vale.
Però no estem veient que tenim diferent.
No me gusta esto de que tengo que elegir en qué ejes hay que sacar.
Sí, o sea, debería de ser como lo más automático posible.
Pero
Està correcte.
pero
Era un poco. No justo lo que minimizaba, ¿no? No le importaba. O sea, escogías un.
es precisamente que tiene que
Pero esto no es. Es raro.
Ya. Sí, está pasando.
Bueno,
No hauria.
sí, yo tampoco. Bueno, sí que había, o sea, sí que lo mencionó en algún momento, pero nunca lo apliqué yo.
Ah, no.
Creo que lo apliqué, ¿sabes? En donde
Això ja era de fora.
yo en el máster de métodos médicos sí lo vi.
És redundant.
Ah, vale,
No, no extremo.
Això està la iniciació sobre la escola.
Sí, aquell guai és aquest perquè jo ja ho sabia.
Sí, extreme es extended frame, ¿no? Que no, tienes elementos cortados. ¿Qué es ese? Donde tienes que ser moving list. Que ahí se hace un smoothing de la solución con regularidad.
Això vull dir, això. Ostres, si té un error, a mi no em podria
Cargar algo bonito, que es bonito. Pues yo le puse 2.0, pero el learning rate. Con 2.0 sí te debe salir un poco más bonito. Mira, o sea, inclusive con esto. Mira.
Sí, pues yo no sé qué tengo mal.
Sí, así me da.
Ara té un shape diferent. Això no ho pots guardar en una matriu, en editació.
Es la regularización que estaba
Podries definir-lo com una opció tridimensional si tingués exactament si tot el mateix tamany, però si no ho és, pots fer una llista, però una llista no pots fer operacions. So most of you should see this plot, this minimization. We find the boundary, and this is what we obtained yesterday without hidden layers and with a polynomial degree of 2. But now we really don't need that polynomial degree. We could set it to 1. We would theoretically we would have a straight line that can't divide the two classes, but we can overcome that just by having some deep architecture in the network. So our network already learns which degree of the polynomial has to be. So we can say d = 1, and for example, even with just one hidden layer, I think it will work. And we run it. We'll see that even with d = 1 and just one layer, it's already doing this boundary. And to obtain this boundary, yesterday we have to put d = 5 or d = 6. And if we keep increasing the number of layers, I don't know what will happen, but theoretically we will have more capacity.
So, for example, 4 is the size of that layer.
Oh, yes, these are just the hidden layers.
But it's the size when you say 4, 8, 8 is.
Yes, it's what I said before. We have this vector topology, which the first is always the size of the index that you have, the last the size of the classes. If we remove all the hidden layers, we resemble the logistic regression. We don't have any hidden layers. And if we add hidden layers, these numbers, it's just how many units, logistic units you want to have in that layer. So for example, this network would have 2 entries, then 4 logits, 8 logits, 8 logits, 3 logits.
Okay.
So we are adding a lot of parameters to the network. So it has more capacity.
It overfit.
Yes. And with 4, 8, 8, it's doing this plot. So we can introduce some lambda and it would regularize and all that. So we can move on, I think. And the next is the iris dataset. So we will see an example of multi-classification. And as I said, we have the correlation matrix, so we can see which variables we'll use, which probably 3 and 4, or 2 and 3 in Python node. So these are the index, which variables we want to use. We want to use 2 and 3, so these ones. And something that Alex didn't explain, and I think it's interesting, is that if we are using sigmoid here in the output,
remember that when we did binary classification, we said, okay, we use a threshold function which gives 0 and 1. And then we decided we want to have a differentiability. So instead of threshold, we'll use sigmoid. And this would be an interval. So we can have any number between 0 and 1. And we can give the interpretation of the probability. So if we get an output of 0.7, we can say, okay, the model is 70% sure that it's from this class, and it gives 30% probability that it's the other class. But if we are using sigmoid in the last layer, every single, since they are independent, every single unit could have any number between 0 and 1. This one also 0 and 1, and this one also 0 and 1. So, and they are independent. So here we can get, okay, 0.4, 0.9, 0.8. And what does this mean? Like, okay, we are saying 90% probability of belonging to this class, but 80% of probability to belong in the other class. It's a little bit weird. So we can just use it like, okay, the highest is the one that it really thinks. And for example, we could take the sum and the average to see the proportion. Or most of the times in the last layer, instead of sigmoid, there's another function which is called softmax, and it already computes the average of all the functions. So we get an output that it's already average, and we will get always the sum equal to 1. So for example, the possibility would be 0.6, 0.2, and 0.2, but all of them have to sum to 1.
Yes, and you can say that it's a regular version of the maximum, which is not differentiable, but the softmax, it's called because of this, because you can differentiate it.
It's a softmax version of the maximum, yes.
So it's like your sorry, I forgot the word. When you sum everything on the vector and then divide by the sum of everything, how do you say that? Yeah,
Normalize it.
Yeah, it's like a soft normalization of the.
Yes.
Okay. Yes. Thank you for the. It was going to stick in my mind.
Okay, so since we already programmed forward prop and back prop, we can just try again what happens using different parameters to this network. For example, since the boundaries are the three classes are easily separable, it just decides that the simplest solution is the best, and just to get straight line here and straight line here. And for the red, it has two straight lines. One is here and the other, we can see it more or less, but it's just like together with the green one, it's just under the green one. Yes, so it decides to classify it this way. And for example, we could try the logistic with equal to see the difference. So this is, it can just use parabolas or ellipses. And we can see the minimization, and we can also play around. Let's put again a neural network. And we can also play around with the learning rate. So we set it very small. It will not minimize. Like we have gone from 235 into 231 in 10,000 iterations, and it's far from convergence. And on the other hand, if we set it too large, for example, 2, which is really big, it should not converge also, I think. So it's converging. But we could put it even higher. And it's kind of exploding, but it also, we have a robust model, and the step size is also getting a little bit noisy. So for the last part, I just wanted to show the stochastic gradient descent variant. In these data sets, it really doesn't matter because we just have, like, both are like 100, 200 points, and it doesn't matter that much. But we can see what happens. So I already introduced it. We don't have to code anything, but we can check the difference with gradient descent. So here we called it yesterday the gradient descent. This is the update formula. It's the same for stochastic. But now we will take 2 loops. One loop will be through the epochs, and the other one will be through the iterations. So essentially what we are doing is we have a big data set, like with lots of points. Just write some of them. Okay. So we are saying, okay, instead of using all of them to compute the gradient, just take pairs. So these 2 compute the gradient, with these 2 compute the gradient, with these 2 compute the gradient. So for us, every iteration is every time we compute the gradient. So take these 2, compute the gradient, 1 iteration. These 2, another iteration, another iteration. And when we have passed through all the data, we say that we have done 1 epoch. So all the data has been used to compute the gradient, but separately. So it's less expensive. So this is 1 epoch, and then we can do it again and again and again. And something that we use, that it's usually done is that in every epoch, it's random how the data is paired. So we don't always have these 2. So for example, in the first epoch, they are these 2, these 2, these 2. But in the second epoch, this one will be with this one to compute the gradient, and this one with this one, and these 2 together, and every epoch is random. So what we do is just to create a mini batch from the whole data, and we say that to be x and y. So this function, what it really does is to take a random sample from all the data, and we use that to compute the cost and the gradient, and we keep iterating. So in the last cell, here we have again the same minimization with this data, with the same structure. And we can see that we are using here, the batch size is m divided by 1, and m is the shape of x, so all the points. And when we have all the points, it's smooth, it's always going downwards. We are using the gradient, so we are going in the steepest descent direction. But if the batch we set it instead to m by 2, for example, so every time, every iteration, it will just use half of the points to compute the gradient. We run it. We'll see that there's some noise. Now it's not ensured that we will get a gradient in the descending direction, because we are just approximating the gradient. So it can be some noise when, okay, you said the gradient is this direction, but it really wasn't. So the cost gets a little bit up. And if we could say even, for example, the batch to be divided in 10, which is a lot for a small data set, it will be even noisier in theory. Okay, so forward propagation is, I didn't put pseudocode, but it's just the concatenation of these two equations. So we take a for loop through the layers of the network, and we do, okay, hypothesis function, activation function, next layer, hypothesis function, activation function, next layer, activation function, we arrive to the last layer, and with the last output, we say, how much is the error? And we compute the error with the negative log likelihood. And you see, this is with, but it's pretty awesome because we have a data set of 150 points, and we say compute the gradient just with 15. And with 15 points, it's still descending and more or less converging. We find a solution. But have you seen that for running with 10 different batches, so we divided by 10, it took 30 seconds to run this cell. But if we put by 1, it will be faster or slower? What do you think? In theory? In theory, it has to be slower because we are computing the gradient with more points. But in practice, what happens is that it was much faster. Can anyone say why? Why do you think it was faster? Because in theory, we implemented stochastic gradient in the sense so we can be faster. But why it wasn't faster?
Because it needs less iteration.
Yes, exactly. So the way we define it, the iterations, when we, this is because we define it like that, but if we are setting a number maximum of epochs, not iterations. So if we divided more the data set, more smaller, we will have to do more iterations because to complete one epoch, we'll have to do more computations. And for this data set that it's small, it's not that big difference to compute the multiplications with 10 points or 100. But when you have 10,000 or 100,000, it will be much faster to have stochastic gradient descent. So for the no questions. So for the programming, I think we are done. That's all that I wanted to show today. But any questions about that last part? Yes.
What are the limitations for the hidden layers? What is the minimum size or maximum size?
Yes. A lot of people asked that to Alex in the previous, and he said that he doesn't have any idea, and me neither. I don't have any idea. There isn't any limitation computationally.
I mean, is it a good one?
Yes, it would. Okay. But you're reducing all the data to just one dimension. So usually what you do is you try to doesn't have really big jumps. So if you have an input size of 10,000 samples, you don't go and say, okay, second layer, two, because you are just compressing the data too much in one jump. Usually what you do is, okay, first layer 100, second layer 300, then 100, and like the last layer has to be the classification. In the last layer, okay, if we have 3 classes, 3. So we don't get big jumps through the network. But we can define any architecture that we want. If we don't have that, for example, in one layer 10,000 and in the next 2, it's okay. You can say 10,000 and the next 1,000. It's not There are no hints in how to define your architecture or your topology in a network. With experience and trial and error, you will learn how many layers and how many neurons you have to put in that layer. So as I was saying, for the stochastic gradient descent, what we can see is I can show a graph from my bachelor's thesis that it was with this data set, which is a data set of images, so it's much bigger. It's 10,000 points, and each point has the number of pixels, which is equal to 1,000, more or less. So it's much more big data. And when we run it with a stochastic gradient descent, here what I did was to I set minimization time. Okay, so you can minimize for 5 minutes, and after 5 minutes stop, and what is the accuracy of your predictions. So I did that for different batch sizes. So this last one is 10,000, which is all the data set. And here the smallest one is just use 10 points of the 10,000 to compute the gradient. And for 5 minutes, which accuracy will you reach? So we can see that we have like a parabola shape. Well, these are 3 different algorithms. So stochastic gradient descent is in blue. And we can see that the optimum, it's around 10 to 100 or 200. So with just 100 points of the 10,000, you are going the fastest and minimizing the fastest, reaching the most accuracy. This was the graph similar to the one that we tried with different learning rates. With higher learning rate is faster, but if it's too high, you are not guaranteed to converge. Other parameters. Regularization. Yes, another technique that I can explain very quick for regularization sometimes. In machine learning, it's also really used instead of penalizing the cost and introducing the term with lambda. You can use another time of regularization, which is called early stop. So if you remember, the training error, since you are minimizing, it will go like this. No? But the test error will minimize as well. The test, you started minimizing always a little bit higher than the train. Minimize, but at a certain point, you start to overfit. So it will go up again. It will be like this, and it starts going upwards. So what you can do is at every epoch, every time that you have passed through the data set, you're in the training, at every epoch, you say, okay, how is the test error? Has get down or not? And you keep going and you can go and you say, oh, my test error is increasing, so I stop minimizing and I finish here. So it's another way to regularize instead of using regularization.
Sorry.
Yes.
You are also then fitting your error, aren't you? So you're gonna really rely on that error. Say I have an error.
Yes. So that's another thing that I think that we haven't explained is that during these days we said that we divide in test and train our data set. But in reality, what we do is we divide, okay, test and train, and then our train let's say 20% and 80%, and our train, we divide it as well, and we say again 80% and 20%, and this is called straight training, and this is validation. And the validation is what you really use for this, or to change lambda, because if instead of this regularization you use the lambda, you also have to set the lambda depending on your test. So you do it on your validation. And finally, when you have found your lambda or your number of iterations that you want to train, you again compact this data, train with all of it, and test your error. So your test is not biased by the minimization. And so finally, since we have time, some other results from my thesis is for this data set of the written digits, I got an accuracy of 97% for the images. So the idea is that we have different numbers, handwritten numbers by students from USA in high school, and you give the images and it has to predict if you have written a 7 or 6 or different numbers. So 97% is in fact really near to the highest value obtained with a feed-forward neural network. That's what we just code. Because then in image classification, you can use other tools, which is convolutional neural networks. I don't know if you have heard it. But instead of the hypothesis function, instead of being x times theta, it's more complex. It uses the convolution operation, and there are other structures that can be used as well. Recurrent neural networks, which are not just feed forward, but it has some backward connections. So you try to use all data and you can get better results. And here we can see some of the errors that the network got. For example, in theory, this here is a 6, but the network said, okay, I think it's a 2. I don't know, because maybe it's the lower part of a 2, but it doesn't seem 6. And this is a 2 in theory as well, and the network thought it was a 7. I think it's pretty similar to 7. But it's what happens with real data sets, that some people you have some data that it's not the best to train your network. And finally, I also trained with images of flowers, and this will serve to introduce the practice from tomorrow, because okay, these images from here are in black and white and have 27 by 27 pixels. So as I said, if we use the pixels as our entries, sorry, the data, we have okay 10,000 images, because that's how many there are. And features, if we use our pixels, we have 27 by 27, which will be close to 1,000. It's okay, but if with these images you try to do the same, these images are with really higher quality and are like 500 times 500. So if you try to use your pixels, you are like using 250,000 features. And that's a lot. That's really difficult to minimize with stochastic gradient even, or because a stochastic gradient doesn't reduce this number. Stochastic gradient deals with this number, with the number of entries. So that's not really possible. And what we can do is to treat our data, we try to use another representation of the data. So that's why the representation is really important. So instead of using this, what we could use is the coefficients of the Fourier transform, and just use the most important coefficients. So we truncate our data to let's say just the first 900 coefficients. So it's similar to this one, or that's 1000 first coefficients. So first, what I tried to do was to resize the image like this, which is just to make the average of the surrounding pixels. Say, okay, if you have 500 pixels, just get bigger pixels with the average value of these pixels, and you get this image average. And that didn't go well. It was too much loss of information. And then I moved to the Fourier transformation. And if you take the same exact number of features, but with the Fourier transformation, this is the image more or less, which is way better for the classification. And with the same network that we coded today, but little bigger and some other algorithms, and these images in this data set that has 5 different types of flowers, but lots of images of these flowers. Some of them even have persons grabbing the flowers and all different kinds of stuff. And with this network, I reached, I think, 85% of accuracy. So 85% of the photos were being classified correctly. Instead of with this average, it was just like 40%, which is better than a random guess, because random guess is 20%, 1 of 5, but it was suboptimal. With this, I think it's all for today. I don't want to show anything more. And if you have any questions, I can answer them.
I have one question.
Yes.
Because we saw that if we have a problem of classification with 3 classes,
yes,
we are not guaranteed. For example, one point might have like an output of more than 0.5 for more than one class.
Yes.
However, in the example with 2 classes, even with the two outputs, it seems that each point has only one value of one output greater than 0.5. This is always true in the case of a problem with 2 classes.
When you do it with 2, but you also do one versus the other and the other.
Yes.
So you have 2
like
outputs.
What have we done here before with 2 classes?
Yes. I think if you have convergence during the gradient descent, you are guaranteed, because both problems are dependent. When you're looking one to the other, is the same that when you're looking the other to the one. It will vary a little bit on your initial point, because you won't have the same initial point for both cases. But if you arrive convergence, in theory, you should have the same solution.
So the sum is
the sum will be 1. Yes. Okay, so that's all for today. And tomorrow we will see one of these techniques to compress images, so we can have less features, which is PCA. And until tomorrow.
Recording stopped.
Yeah.